same mth body, but this time I will tell you that how the machine should be done, and how to turn on those transient models like LES and DAs. Okay, and what would be the impact of those things? Okay, first let me open my lecture. Okay, so now if you take a look on the turbulence modeling slides, you will see that the turbulence modeling actually has the three regions. One is the RANS region, one is the LES region, and one is the DNS region. So right now we are concerned with the LES part and are in between the LES and the RANS region. So just go there. Okay, so here you can see that if you're solving the flow, and then this is the first, this part is the energy containing range. Okay, so energy containing range is a range which the body size is there. Okay, so the body size, these eddies will range from the some percentage of the body length to the like multiple times of the body length. Okay, for example, the body length is 1 meter, then the eddy size, the starting eddy size which contains the energy, they can be from the like a 30% of 0.3 meter to the maybe like 10 to 15 meters. Okay, they can grow on the downstream side. So these eddies, like we have to resolve these eddies. Okay, okay, let's again continue. So here we can like solve the eddy size of like a 0.3, 30% of the body length to the multiple times length of the body. So this is energy containing range, and its value is given by the formula. I will tell you right now. Okay. So this is length scale formula, and it is, I think, the k power 3 by 2 upon epsilon. Okay. In terms of the omega, you can find it out by putting the value of epsilon in terms of the omega. So this length, if you call about this length, this is the length of this eddy, these eddies. Okay, these eddies. So once we find out this length of this eddy, so now point is that if you are going for the LES, okay, the LES stands for the large eddy simulation. And please note that the LES is not a turbulence model. LES is not a turbulence model, not a turbulence model. Okay. So it's a method to resolve the all the eddies in the flow up to this range, So this range, like typically speaking, they said that this should be able to resolve the 80% of the turbulent kind of energy or the K. Okay, so this much range should be solved. So now how this can be, like we can make sure that we are solving this much range in the LES simulation. So that is by this trick. Okay, so if the length scale is there, so if let's say the my length scale, energy containing the length scale is like they here, they will be different length, but once we are inside the inertial subrange, they will be of the same size. They will be of the same size. Almost they are asymptotic. They will be reducing, but their change is asymptotic. Means that the every side eddy size will be the similar. Okay. So now if the AD size is like, for example, is one AD is this one, and the AD like up to here, next AD is up to here. Okay. So now what we did is we found out the size of this AD. Okay, length scale of this AD. That's equal to the, sometimes they call the L, sometimes the L naught. So now what they are proposing that if we can make the mesh size that is like 1/6 of this length scale means L naught or L divided by 6. So they are saying that we will be able to resolve this eddy as well. So now to able to resolve this eddy means that the mesh size should be small enough so that that eddy will be inside the those mesh cells. For example, if I make the cell size of this one, so this eddy is actually is smaller than the my mesh cell, and this will not be solved, and rather it will be modeled with the subgrid scale models which are here. So if the like you are making the mesh size that is only able to resolve this much LES turbulent current energy, it means that we are actually lacking, we are having some errors here, not resolving this part as well. So in this case, what we should be doing is that we should be making the mesh size smaller. So for example, if I divide this cell into the 4 parts, now this eddy is basically is inside these 4 cells, and we can solve that eddy through the numerical methods. Okay, so to make the same thing very simplified, what they are proposing is that you should divide the your length scale by the 6, and that should be the your mesh size. Okay, so and one more thing, few more things are there. For example, when we talk about the uh, LES and DS. So what is the difference between them? So let me tell you. Okay. Okay. LES is actually is solving the everywhere with the LES. Okay. So means large area simulation. But problem is that, for example, this body. Okay, let's say this is the similar to the MS body. So in this type of cases, what will happen is that we will be able to if there's a boundary layer here, the boundary layer has a very small size of the eddies. Okay, if you talk about the eddies here, after flow separates here, the eddy size will be of this much. Okay, they will be of this much eddy size. But here the eddy size is very small. Now just imagine that to resolve this eddy, we have to at least make the size of mesh size smaller than this eddy. So this will be requiring very fine mesh. Okay, so that is not it's possible, but it's not very much feasible. Okay, for example, recently the ANSYS Fluent they solved the problem on the full aircraft simulation. Full aircraft simulation, you can see the example on their website, and it contained the mesh size of 1 billion. 1 billion is equal to the 1,000 million. So the Reynolds number was like 3 into 10 power 6 or something like that. Okay, in the millions of the some values. So now to I told you this is in the very first class that if the Reynolds number of 10 power 6, then the mesh size for LES would be almost 1 billion. And if you talk about the DNS, that will be like 38,000 billion. Not possible for today's computer. But even with latest technology, they implied the 40 L40 GPUs, and they are very expensive. And secondly, they will be requiring at least 350 watts per GPU. So now just imagine that how much electricity you are going to consume with the 40 GPUs. Okay, and they ran the case for the 8 hours. 8 hours. So they did a simulation, full LES simulation on the full aircraft with the 1 billion cells at 1,000 million cells in just 8 hours with the 44 L40 GPUs. Okay. So now, what is the point here is that the point is that if you are solving the problem here, and we know that for the MS body, as I told you earlier, that the major drag is coming from the pressure drag. Okay. So the pressure drag is where? Pressure drag is in the wake region here. So now what we can do is that we can solve this region with a rinse and save our space, and this part with the LES. So we make the very refined mesh here instead of like a rinse mesh was very coarse. So we have to make the element size that is compatible to this value, like a k power 3 by 2 divided by epsilon, and then you have to divide this size by 6 again. Okay, So first you have to get the size of this eddy from your range simulation, full range simulation, and then you will convert that mesh based on that results by the dividing the mesh size by 6, and you will get the mesh for the DNS and the other LES. But for LES in this region, you have to be like a, because here the length scale will be very small. So then for boundary mesh will be, it will require a lot of cells. Okay. So recommendation is that either you should go with the DS. DS stands for the detached eddy simulation. It is very much clear that it is a simulation when flow separates. So means that it is only for the pressure drag side of the your drag coefficient. Whenever there's separation, means flow is separated from body, that is called the free shear. It's a free shear flow. So this ES is actually is made for the that purpose. Okay. Okay, so now let's continue here. So, and second method, there are few more methods are there. One is the scale adaptive simulations. They also get the advantage of similar to the DS, and also DS has the some advanced versions like DDS. Why so? Because they found that their DS switches to LES mode very early on. Okay, so they have the like a delayed. So the D first here is the delayed. Then they have the IDDS. So this is like to improve the more like there are some shielding functions, and if they can make it very well, so the shielding function can save you by switching to LES mode very early on. So these shielding functions, like there is improvement here and here. Okay, IDDS or IDS or DES, these are shielding functions actually. Okay, then there are some other methods also. They're like a scale resolving eddy simulations. So let's see this thing. Okay, so we have the this simulation here, and also I will discuss about the time step. Okay, what should be time step for these cases? Okay, time step is very important. For LES, time step is even required will be very very small, because the length scale is small. So therefore, length scale to be small, to solve that length scale, we have to have the velocity very small, and for that low velocity, then definitely we have the very small time steps. Okay, so now from the models, and before that you have to turn on the transient mode. Okay, and I will tell you how to calculate the time step. Okay, now go to first, I will be telling you the first method is from the SST model, and they have the stress blending shielded DS. This is actually an advanced version of the DS, which is provided by the, I think the author of this method is the Florian Mentor, who's also the inventor of the SST model. Okay, FR Mentor, and he was with CFX Berlin, CFX Germany for a long time. And once it was purchased by the ANSYS, now he is also part of the ANSYS. So you can turn on the okay from here. But before that, what I'm going to do is that I'm going to actually make my function, custom field function. Okay, so here you can see what is the formula. So length scale formula is the k power 3 by 2 and divided by epsilon. Okay, and our mesh size. Okay, our mesh size should be at least L naught divided by 6. This is the maximum size we should be having that in the LES region. Okay, now let's solve for our own function. So I'm going to take the turbulence quantities K. Okay, so put the bracket K, and power 3 by 2 is means 1.5. So let's put the power as a 1.5. Okay, then the bracket close and divided by the epsilon. So this is turbulent dissipation rate is epsilon. So select here and say this is our length scale. Name of the function is the length scale. Okay, define. So this simulation I ran from the previous class. I ran the completely this simulation, and drag coefficient, they are all are converged. I will discuss about the first drag coefficients also. Okay, so let me open the my slides. Okay, let me open the slides. Okay. Okay, for this case, from the first reference, the drag coefficient is 0.285. Okay. And from second reference, it's a 0.299. So let me show you here. Okay, drag coefficient is 0.285 and the drag coefficient from second reference is at 2017, 2011 paper. So drag coefficient is 0.299. Okay, and lift coefficient is 0.345. So let's see the what values we have for the these parameters. So for the lift coefficient value is a 1.138. Okay, not correct. Drag coefficient is a 3.323. So how much error is there? So calculate 0.323 minus 0.29. Let's say have the second reference. Okay. Divide by 0.299 and multiply with 100. So it's 8% error. Okay. And as far as the lift coefficient is concerned, so its value is right now is a 1.13 and actual value should be how much? Its actual value should be equal to the 0.345. That value I obtained in the my other simulations with the finer meshes. Okay. So in the finer meshes, my drag coefficient was also very much close. Okay. So see here. So I made the mesh enablement study and my mesh size changed from the 0.289 million, 0.58596 million, 1.15 million, 2.15 million, 3.95 million, 5.67 million. So you can see that we have the like something like a error is like minimum error is a 2.8%. Okay. And at that point, the drag coefficient was equal to the there you can see here drag coefficient was 0.9293. Okay. On the last two meshes, the drag coefficient was almost 0.293 and the reference value is a 0.285 from reference number 1. Okay. So any questions so far? Okay, so now I'm going to I'm going to okay, so we will talk about the lift coefficient maybe in some other class that I will let you know. Okay, but right now we'll try to finish up the our course from the like from the today's class, and also I'll discuss one thing in the NACA doubles NACA 2412 aerofoil about two different angle of attacks and how to plot the CP plot. Okay, so here if you go to results and the contour plot and just go to the custom field functions length scale. So here what you see here, I'm just plotting on the mth body, which is going to show me the its value. It's a global range right now, so it's turned on. So if you turn off the global range will show you the value in the whole domain. Okay. So on the mth body, the length scale will be very, very small actually. Okay. So if I talk about this length scale and divided by 6, so my element size will be very, very small that I cannot afford. Okay. So I'm talking about the my element size in this region. Okay. In this region. So where? In this part. Not in this part, but actually, I would say in this part. And up to this point, I'm interested. Okay. Because the majority of the wake region is here. So I need to resolve the mesh over here. So already I made the, if you remember, I already made the density box here. So I just need to get the idea about the length scale. Okay. So the length scale, maximum length scale in the domain is equal to the how much? Is the 0.18. Okay. So if I divide by the 0.181 divided by 6. So my maximum element size should not exceed the 0.03. Should not exceed the 0.03. So now let's open the mesh file and see what size we provided in the back side. Okay, in the rear side where we have the wake region. Any questions so far? Any questions, please?
Sorry, sir. How did you calculate the eddy size or?
The eddy size, it is from the formula that is empirical for like as based on the turbulence theory. And this tells us that this is like given in the theory in the very first lecture I took in February 17. Okay, so that is like length scale is given. It's a very beginning of the turbulence modeling we learn about this thing. Okay, so the length scale formula is actually is here. Okay, so length scale is given by and how I got this formula. This formula is derived based on the on the dimension analysis. So I know that the turbulent kinetic energy is actually is a sort of kinetic energy. Its units are the length square upon time square. Okay, meter square per second square. And the dissipation rate is actually is the rate of the dissipation of the turbulent kinetic energy. So it's a 1 divided by the time again. So this is the L square upon T square K, epsilon is L square upon T power 3. So now if I want to find the function for the length scale, okay, length is the size of the AD. So I can write down the L as the K power N and into epsilon power M. And I don't know what is the value of the N and what is the value of the M. So I just put the like my K, which is L square upon T square, length upon time, and power N, and AD is the L square upon T power 3, power whole power M. So just solve them for the here length scale has a time scale. If I put time scale here, this will have the power 0 because T power 0 will be 1. So length power 1 is equal to the length square power N and the length square power M. So now I can say length square is a 1 here on the right side. This will be equal to the 2N plus 2M. Similarly, for the time powers, for the time, the coefficient powers are the here. So power here on left side is 0. And here the power is in the minus value, minus 2N and the minus 3M. Solve these equations simultaneously and we get the length scale formula is this one. Okay, clear? So then I just made my custom field function. I just went to the physics. Okay, sorry, user defined. And here is the custom field function. Simply click here. Also, we have definitely we have the here UDFs also, expressions also. But I'm just using the custom field function. It's a just simple calculator that will take the variables from the built-in functions, variables from the Fluent. Okay, so just select them with like a click here. If you want to apply some operations, powers, absolute, logarithm, sine, cosine, you can do it also here. Okay, so I defined that function. That function is like a length, turbulent kinetic energy power 3 by 2, which is a 1.5, and divided by the dissipation rate. Simple. Okay. So now I have this value, and if I want to like pinpoint the area, maybe I can just get the one region, volume region through the adaptation part, and I can get exactly what is happening with the length scale in this region. Okay. But just right now, I will just go with my maximum value here. So from here, you can see my maximum length scale is a 0.18. So if I divide by the 6, so 0.18 would be equal to the 0.03. Okay. So just make sure that in the our density box, this is a density box actually, this is the one here, BOI. Okay, so in the BOI, the size we have put here is 0.02. Okay.
और
Yes, please.
कभी तेरी याद आई मैंने कहा फिर तू वहाँ
Okay, so already we get the size of the 0.03. Okay, so now let's run the simulation and see can we resolve the our eddies or not. Okay, so and now time scale. Okay, time factor. What should be time factor here? Now similarly we have the time factor scale also we are given here. Okay, so time scale we can find out, but I am just going to give you very simple example here. Okay, now let's say my eddy size is going to be the like 0.18. Okay, let's make it 0.1. Okay, so 0.1 is the length of the my eddy. So let's put the length of the eddy as a 0.1 meter here. Okay. And the velocity of my flow is 40 meter per second. Okay. And let's say it has to travel like around distance of the how much? Uh, it's like around it's I would say maybe it's a 2 or 3 lanes. Okay, 3 lanes means that 3 meter. Okay, so 3 meter is a distance. So if I divide the 3 meter, so I know velocity is equal to distance upon time. Okay, so time would be equal to the distance upon the velocity. All right. So distance is a 3 meter and velocity is a 40 meter. So if I divide by the 3 by the 40, how much velocity I'm going to get? So 3 divided by 40. So the time would be the 0.075 seconds. Okay. So 0.075 seconds. So time is the 0.075 second. This is like if you move this complete flow from here to here. Okay. Definitely if you take this consideration about the eddy that it should be moving with the some like a distance. Let's take the distance of overall distance with the flow velocity of the 40 meter per second. So definitely, I don't want to cover this whole distance in a one go. Okay. So I don't want to cover this whole distance in a 0.075 second, but I want to move in the like steps here. Okay. So steps of the maybe 0.1. Okay. So let's divide this time into the like 100 steps. So 100 steps means that the flow will be going in this way. 100 step means that the 3 divided by 100 will be equal to the 0.03. Okay. So 3 meter distance will be covered with the steps, each step of equal to 0.03 meters. And it will take the time of the how much? 0.0075 seconds. So each step of 0.03 meters will take the 0.0075 seconds time. This is a time step actually. Okay. So time step. So it means that now I'm going to provide the time step of 0.0075. But if you are going to run the LES simulation for the complete problem, just to give you idea, because the AD size here is very small. So in the case of LES, the time step might be is a 10 power minus 6. So here it's around 10 power like minus 3, around that value. Okay, but in the LES simulation, this will be around 10 power minus 6. Okay, so not only that you require the more number of elements here, but also your simulation will take more time to converge for the required time. Okay, so now clear that you're drawing from here, and for the time step is equal to 0.007. Okay, so here run calculation. Time step size is a 0.007, and number of time steps are, let's say I'm going to run for 1,000 steps. Okay, and also you have to like turn on the some of the models. For example, you want to run the DA simulation. In the DS we have the delayed detailed simulation, means the DES. Okay, uh, so this will be the DES, double DES. Okay, also you can turn on the IDDS. Okay, so it's your choice. So by default, the delayed detailed simulation is turned on, and it is based on the SST K omega model. But also, you can run the Arians model as a Spalding-Morris model, or you can run the realizable K epsilon model. So generally speaking, the SA model was the original one who invented the DS, and then the SST is also there. So you can either go with the traditional SA DS type, or you can go with the SST K omega DS. Okay, and then you can click on the OK. If you want to go with a large eddy simulation, then we have the like well model. This is for subgrid scale. Subgrid scale means that for the smaller eddies, like after the Taylor scale. Okay, there are 3 scales actually. So there are 3 scales. So energy containing range. Okay, this is the inertial scale. Then we have the inertial subscale, and also we call that scale as the Taylor subgrid. And then we have the Korolov scale, that is a dissipation, means that when the eddies are actually being transformed in form of the heat energy. Okay, so in the LES, what is going to happen is that they are not going to the like this range, but then rather they will stop here somewhere here. Okay, And then the eddy size, smaller eddy size, they will model through the. So now this is modeling now, like a turbulence modeling. This is a turbulence modeling type of thing is over here. So here they will solve up to this point, and after this point they will be modeling them again, the modeling approaches. Okay, this is called the subgrid scale models. There are many models are available here, so you can choose one of them. By default it is the Wales model. Okay, so also we have the VM LES, VM LES S omega. So the very common one is a Whale or the Smorgasly Lily model. Okay, so you can use any one of them. I would recommend any of these two. Okay, so then they will change some default settings, for example, for the like a solution scheme like those ones. Okay, so let's use the K omega SST model and use the latest one, that is the stress blending shielded DS simulation. Okay, so this is a stress blending eddy simulation. So full form SBES is the stress blending eddy simulation. All right. So here we are using this one, a stress blending eddy simulation. This is eddy viscosity, is like eddy simulation, and a stress blending, that they are blending the two approaches, Rance and the Ellis approach in a single approach. Okay. So click on OK and then run your simulation. Simple. And you will see one thing, that the here the our convergence plots, residual plots, they will not be like a straight lines like a range, but here they will be changing. Okay, they will go down and then again after every time step they will go up, because every time step they have the different values, so they are converging in a single one time step to the final values. Then for again for second AD, they will be again solving the from the very beginning. So that's why they will go up and down after every time step. Let's stop here. Okay. Okay, I'm stopping here and I'm going to actually get my old results, okay, with the finer mesh. So here it is the like new ML body case.
Sir,
Yes.
why did you take the length scale or the eddy length scale from the wall, not from the domain beyond
No, I
or
didn't take the from the wall, because if I go with the wall size, that will require the very fine mesh. So in these methods, like a DS type methods, we are going for the only like a part that is in the wake region, in the pressure drag. Okay, the free shear flow. So those are the bigger eddies than the eddies we have in the boundary layer. So we are after the like only because the eddies are playing the most important part in the wake region, not over there. Okay. So just 1 minute. Okay, here. So actually, I believe that I ran the case over here. So double click here. And mesh size was very fine in this case, in these two meshes, mesh 5 and mesh 6. Okay, now the question is that once we like solve the problem, so how to get the our like plots? Like sometimes people show the what is the plots on the body in the whole volume. Okay. Okay. Also, I would recommend that just go to the some like papers where they talk about the how to resolve 80% of the turbulent kinetic energy using the LES simulation. Okay, so once we can find out that we are able to solve the 80% of the kinetic energy, then we are sure that we have done the correct LES simulation. Okay, but if we talk about the DS simulation, then again you have to like apply some formulas to assess how much energy we have resolved actually by our mesh. Okay. You can see that we have the like SBES simulation run here, okay, shown here, okay. So just a minute. And also we are going to be having the heat transfer course today at the 6:30 p.m. Pakistan time for the students who have early enrolled for the heat transfer course. Okay, so here I will send you paper where they are discussing about that function, that how to access that we are able to 80% resolving the 80% turbulent kinetic energy. But here I will tell you that how you can actually plot those vorticity plots. Okay. So first thing is that let me display my mesh. This is half model because we made the symmetry, took the advantage of symmetry. This is half model. And if I talk about the road and put the mesh here, also on the symmetry, you can see that we have actually very, very fine mesh in the back region. Okay. So we have a very fine mesh in the back region. And in the mesh number 6, it's a very, very fine actually. Very, very fine. Okay. So very small cell size like a 0.01 or maybe 0.008 like that is in the back region. Okay. So in order to get the like those plots like you have seen in the some papers or some internet on the internet. So first thing is that I will go to the create and isosurface. Okay. Then I will go to the turbulence from here. Not turbulence, but rather I would go with the velocity variable, and I will go for the Q criterion. Okay. So Q criterion here. So just compute. Okay, put the value. This is a trick here. So put the value of 500 only. So you have to check which value is going to work for your case. So just put the right now value as a 500 and click on the create. Okay, now this is a very tricky thing. So this trick I learned from the official ANSYS website. So they use this value. So you can vary this value for other cases, maybe will be different value. But I thought I feel that this value is very optimum value. So go for the 500 and click on create. Okay. Then go to the contours and then click on the velocity, and this time go for the vorticity magnitude. Okay. So and where display your geometry. Okay, let's make the complete geometry display, so you can like turn on the symmetry and click and apply, and this will show you the complete geometry. And if you want to change the color to the traditional default colors, that will suit more here because we are going to display the vorticity in the different colors. So in this case, the geometry should be in the gray color. Okay. Now I will be clicking on the Q criteria and normalize where our value was equal to 500. Okay. Now just click on the compute. You can see again the values are varying from the very large values, varying from the minimum to this value. Okay. So I'm going to click on the range. Okay. So because this solution, okay, so put the value from 0 to like 1000. Okay. So like this. So this is the how you can display the your vorticity magnitude. Okay, it looks like the solution was like not run completely. Okay, otherwise we would have the these vorticity mechanisms. So I usually speaking, I use the values from like a 5 to the 500 or 700 or 1000 maximum is that value. Okay, this is a trick how you can display the these plots. And similarly, I have plotted this. I have shown the same velocity plots in my results here. So you can see that the velocity like a curl, which is the vorticity. So it varies from 5 to 800. Okay, 5 to 800. These ones. Okay, now the question that, for example, how to be make sure that we are resolving 80% of the turbulent kinetic energy. So alias 80% of turbulent kinetic energy for CFD. Okay. Okay, so I will be sending some paper that will tell you that you can how you can be make sure that you are so resolving the 80% of the turbulent kinetic energy. Okay. So any questions about this topic? This is very brief overview about the LES and DES and the scale resolving simulations. So what are your thoughts? Any comments or any suggestions? Any feedback? Any questions? No questions? Okay, so I will now switch to the my second problem that I solved the problem completely, but I feel that this was not a complete knowledge given to you. So that's why I am going through the NACA 2412 aerofoil case. Okay, so right now I'm going to talk about the two things. Okay, so can you see my screen?
Yes, sir.
Okay, so the first thing is that the angle of attack. Okay, how to provide the angle of attack. Maybe you know this thing, angle of attack, and then how to find out the corresponding drag coefficient with the angle of attack, or lift coefficient. And secondly, the CP plot. Okay. Okay, so let's say this is the my zero angle of attack case. So open solution from here. Okay, so when you talk about the CP plot actually will tell you that the how the pressure is changing on the aerofoil surface. So in case of acceleration on the surface, you will see the negative pressure. In case of like a stagnation point, you will see that the pressure will increase. CP will increase above the zero value. Okay, so above the zero value means that the pressure is increasing, and below the zero value means that the flow is accelerating and pressure is going down, velocity is increasing. Okay, so in case of the aerofoils, they definitely will have, especially the camber aerofoil also will show you the CP plots on zero angle of attack. Okay, for symmetric aerofoils, they will show you straight line in case of the CP plots. Okay, means that the upper and lower surface will have the similar results, like maybe this, like this, or maybe this. Okay, but in case of camber aerofoil, you will see that there is like some change in the pressure as well. So for this case, I will make a one line on the middle of this aerofoil, okay, in between the two symmetry planes. And to plot the CP is actually is equal to the P static minus P. P static is the free stream pressure on the inlet. Okay, that is the in case this will be the 101.325 or maybe 0, and divided by the dynamic pressure 1 upon 2 rho V square. So what is requirement is that you should provide the reference values correctly. Okay, that's all. And you can make your own function as well. Okay, that is using the custom field function. So you can make your own function also. So there you can define like your pressure minus the some static pressure at the inlet divided by the dynamic pressure. You can also use the values directly inbuilt in the functions here. So I can like go there, and we have the like for example, I'm plotting the xy plot. Okay, so I do have the pressure coefficient option here, but this will require that you should be putting the correct values there. So in the reference values, make sure that we have the correct values provided on the inlet. Okay, so everything is correct. So now I need to make the one line here. So for that, I will go to the domain or directly from here create and iso surface. And on the aerofoil, this is 3D aerofoil. So if I put the constant Z location, this will get the one line from the aerofoil. Okay, so I'm going to put the variable as a mesh and sub variable as the Z direction. Okay, if you compute this varies from 0 to 0.3 because we have put the thickness of the third dimension of the aerofoil as a 0.3, 30% of the chord length. So put the value as the 0.15 and put the number is a 0.15 here. Okay, click on create. Now, if you take a look on the this mesh here, along with this new line Z.15, you'll see over here. Okay, this line is over here. So we are going to plot the CP plot here, and for cambered aerofoil, like a 2424 denotes that the 2% camber, and at the 40% of the like a chord length, we have the that maximum camber is there. So in these cases, cambered aerofoil, they will show you the CP plot at 0 angle of attack, and means CP plot actually also in simple words, it's also indication of the lift. So if there's some like a change in the two sides of the your aerofoil and you see some difference in the CP plot, it means that you are getting the some lift coefficient over there. Okay. So CP plot, and I'm going to display along the x-axis what I'm going to display the pressure coefficient, where I want to display on Z.15. So this is what I'm talking about. Okay. Okay. Now, can you indicate the which line is showing which one? So the typically speaking, when you see the plots, what they do is that they flip the axis. They flip the axis, and negative axis will be on top side, and positive axis will be values will be on the bottom side. So one is showing the stagnation point because all the dynamic pressure has changed. For example, here this P is equal to P static minus P divided by the some dynamic pressure here. So it converted all dynamic pressure into static pressure. That's why you are getting the value of the one here. Though this is like on the lower side, and on the upper side, this upper side actually that's why we always flip the these plots. So you have to like export data into the Excel and then flip the axis. Okay. So you put the positive values on the bottom side, negative value on the upper side. So this shows the upper side of the aerofoil. Where actually we have the acceleration of the fluid there. Okay, with the velocity will be higher on the upper side and velocity will be lower on the lower side. Okay, so that's why we have to flip that one. So this should be shown on the upper side, and this will be the different. This will go on the now in bottom side of as compared to the upper side. Okay, so then we are going to run the case with our angle of attack. Right now, this is the angle of attack is 0. So I will duplicate. Okay, and I put the name as the angle of attack 10 degrees. Okay, so double click on the solution. Okay, 10 degrees because for the 0 angle, we know that the cos 0 is a 1 and sine 0 is 0. So for 10 degrees, we have to provide the two components, cos component and the sine component. Okay, and secondly, you have to be careful that in which direction you have to provide these values. So let me show you that where I'm going to put the cos component and where I'm going to put the sine component. Okay, so first I will change from the boundary conditions. Okay, now see that the aerofoil angle of attack is defined by the this way. Okay, so this is like this is our chord line. Okay, chord line is joining the leading edge with the trailing edge. And if I provide some angle of attack, so that angle of either I can put the angle of this angle of attack is between the air and the chord length. So if I put the my aerofoil some angle like this angle, it's a chord here, and I put the same flow angle here. Okay, so still I get the some alpha there. Second way is that I will keep the aerofoil chord line at the same location, but now I'm going to provide the my flow from some angle below this one. Okay, but still you can see this is my air direction. This is my air direction. This is my chord. This is my chord. So the in both cases the angle is definitely the same. So either way you can like a turn tilt the your aerofoil, but then you have to make the new geometry, new domain. Slightly maybe you can take the advantage of the inbuilt functions of the design modeler. Then you have to make the new mesh. You will not be maybe not going to define everything from the scratch, but still you have to generate the mesh on the new geometry. So the better way would be that I'm going to provide the angle of attack. Okay, so this is same thing. It will be having the same like alpha, same alpha here. Okay, so now I'm going to provide the angle of attack from in this way. Okay, so my chord length and my flow, this is the air, alpha is there. This again is a positive alpha. Okay, so positive alpha is that when the your air is below the your chord line. Okay, negative alpha is that when the air is coming from the top side and your chord line is below that line. Okay, this is a negative alpha. Okay, so and also you can see that the two axes which are involved here are the axis and y axis. So in this case, we are going to provide the, like here this is the x and this is a y. So in this case, if we talk about the angle of attack like 10 degrees, so the sine component will be in the y direction. This will be sine 10, and cos component will be on the x axis. So this will be the cos 10. And for z axis, we just put the 0. Okay. So here I'm going to put the angle of attack there. So copy this one, select all, and then copy. Okay. And put the x component here. Then I'm going to again put the 10 degrees, and this time I'm going to use the sine function and copy and place and the y component. Okay, now you have to just change your lift coefficient and drag coefficient also. So you have to provide the same angles here as well. Okay, if not, then the values you will be getting the convergence plots, but they will tell you about the convergence, but value will not be correct. Okay, so simply run the calculation. Okay, in this case, I would suggest that we should stop the simulation. Okay, and reduce the time scale factor maybe to the 0.5 first. Okay. So values here, they are shown, they are wrong values, but definitely whatever value is there, if they stop to change, it means that we have now got the convergence. Okay. So negative drag coefficient, it indication that we have the wrong angle of attack. Only thing is that. But in any case, if they become a straight line, means that now they are converged fully. So from there we can say that now solution is converged fully. So even with the wrong values, we can still have the convergence assessment. Okay. Okay, I will just stop here. So maybe you have to run the case for the more iterations, but I will stop here. So I will show you that how to get the lift coefficient, drag coefficient for angle of attack. Okay, select the airfoil. In this case, I have to put the angle of attack there. Simple. Okay, for drag coefficient, it will be exactly 10 degrees in the x component, y component is the sine component. Okay, so this value will go in the x component. The cos component will be in the x component for the drag coefficient. Okay, and same 10 degrees and cos component will go into the y component. Okay. So the drag coefficient is a 0.67. It may not be correct value because we have run the simulation only for the 20 or 17 iterations. Okay, as far as the lift coefficient is concerned, so we have to be very careful about the angle of attack. So what is the actually the how this can be defined? So see, for angle of attack, what is going to happen is that this is our aerofoil. Okay. and we have provided the angle of attack here. This is the chord line, okay. Alpha is here. So by definition of the drag coefficient will be displayed same direction as the direction of the your flow. This is your drag here, okay. And the lift will always be the normal to the your angle of attack or the your drag coefficient, okay. This will be here. And in case when you are like a traditional way of aerodynamics that they are being applied at the 30% of the coordinate. So this you can show the same angle, but in this case you will show the drag and lift in this way, okay, from the 30% of the chord length. Okay, so now what about the lift drag coefficient? Drag coefficient will be now converted into two components. One will be the x component and one will be the y component, okay. For the x component, this will be like with the angle of attack, so cos 10, and here it will be the sine 10. Simple. Sorry, not here, but this angle of attack 10 degrees. So in the x value, we have the like cos 10, and the y component we are going to have the sine 10. Okay, now just take the example of second case, the lift coefficient. So lift coefficient is defined on this side. Okay, so positive y-axis is here. It's a lift. Positive pi is here and positive x-axis is here. Okay, so in this case definitely we are going to resolve this uh, the lift coefficient two components. So one will be the y component, one will be the x component. X component now this way because this will be on this side. So this is our the y component, this is our x component. Okay, now like we have the angle of attack here with the lift coefficient with the x-axis 10 degrees. Now same angle will be made right now with the lift part with the y-axis. Okay, so 10 degrees. So in this means that the and you know from very basic of trigonometry, where the angle is there, you have to like put the cos component there. So y will contain the cos of 10 and x will contain the sine of 10, and you know that when the angle is negative, cos will give you same value, no sign change. But when the angle is negative on the like a second quadrant, the x component will be negative because of the sine function here. So this will be like you have to write down minus sine 10. Okay, if you're just checking magnitude here, you have to put minus sign here. So now what will be changing is that in the drag coefficient you put the x and y here like this, cos of the theta
So,
and sine of theta, and
so
this
I
is for
think
drag. Yes.
so I think the screen is frozen.
Yes.
I think the screen is frozen, like the recording is frozen.
uh I'm sharing again.
Okay.
Okay, now it's okay.
Yeah, it's all right then.
Okay, so again, should I repeat this thing or everything from here?
Yes, okay. If
Okay, so this is aerofoil. I'm just will go quickly. This is my chord line. Okay, so the lift drag will always in the same direction as my direction of the air. This is right now for zero angle of attack. This will be this drag will be here, and lift will be normal to the drag coefficient. But for angle of attack, the drag is here because the same as your angle of attack, and lift will be normal to this one. Now, as far as the drag coefficient is concerned, so x component will be with having the cos of the angle, and y component will be the sine of the angle. Okay, but left side, if you go on the left side, you will see the angle, same 10 angle is making with the y-axis. So the y-axis now, because making with the 10 angle with the y-axis, the cos component will go there. This is from very basic trigonometry, and sine component will be go on the opposite side of angle, which is defined there. So it will be the sine of 10, because now the second quadrant, the y is a positive value and the x value will be negative. So for drag, we have to put the x as a cos theta and y as a sine theta. For lift, we have to put the x as the minus sine theta and the y as the positive cos theta. Simple. Okay. So therefore, I'm going to calculate my 10 degrees of the cos, and I will put that one in for the drag coefficient. I'm going to put that one in my y-axis. Okay, so cos will go to y-axis, and x will get the minus of the sine 10. So 10 of the sine minus value already I put there. So copy this value from here and copy. Okay, and paste here and print. So this will give you the lift coefficient. So drag coefficient was there and lift coefficient is over here. Okay, there's difference between the plotting these two values. Now as far as our CB plot is concerned, just make sure reference values are okay. Our line is defined, which is not defined here, so I have to define it again. Isosurface, and on the airfoil, and it is along the z-axis. So, and you understand the method in the frame from the previous case. Put the value 0.15. So the z coordinate, this one, new one. Okay, now this is CP plot for 10 degrees angle of attack. So you can see there's a much more difference between the lower side and the upper side. Again, you have to fill up the axis. Okay, so I have to plot the pressure coefficient. Okay, you have to fill up the axis. Okay, now let's display some values here, some contours here with this angle of attack. So what you see here, you can see now the stagnation zone is being made on the bottom side. Okay, because flow is striking here. Similarly, you can display the velocity. Okay, so low velocity is here because this is stagnation point here. So pressure will be maximum and the velocity will be minimum. And if you and you can see that some separation zone is occurring here as well. Okay, now simply display the vector plots and draw the mesh and local scale, display only on symmetry 2. It's not separated, but it's almost close to separation. Okay, if you increase the angle of attack to 15-16 degrees, you will see some separation there. Okay, you can see that the flow is striking here. So you can reduce the scale to the 0.2 or 0.3. You can see the flow is striking here on this. Okay, this is because of angle of attack. So a 0 angle of attack will strike the flow here, and with a 10 degrees angle of attack, flow striking there. And on the upper side, we have the acceleration. Okay, let's make it 0.1. You can see we have the acceleration on the upper side. Okay. So this will officially conclude the 2 weeks course, and I will be sending you the certificates. And meanwhile, you have any questions, please do let me know in the WhatsApp group or on my private WhatsApp number or in my Gmail ID, which I provided in the on the registration form. Okay. So any questions? No questions?
For me, it's okay. Thank you, sir, for your
Thank you.
efforts. And
thank you.
Thank you.
See you in the next course if we have the luck. Okay. Thank you.
Okay.
Bye-bye.